A'udhu billahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Dear student, Assalamu alaikum wa rahmatullahi wa barakatuhu. Today it's our 12th lecture of powder X-ray diffraction, and the course is X-ray diffraction techniques. Course code is 5134. Dear student, the key concept of our two-day lectures are Oak Ridge Associated University Museum collection for X-ray and gas discharge tube, then introduction to gas discharge tube and cold cathode X-ray tubes, then we will discuss gas discharge tube basic and some detail of these tubes. After that, we will discuss cold cathode X-ray tubes, first cathode, then anode and anticathode. We will discuss in cold cathode X-ray tubes. Now, Oak Ridge Associated University's Museum collection for X-ray and gas discharge tubes. Student can see different X-ray and gas discharge tubes at following web address. स्टूडेंट ये आपके पास वेब एड्रेस दिया गया है। यहाँ पे आज तक जितनी आपके पास एक्सरे ट्यूब्स हैं ऑलमोस्ट डिस्कवर हुई हैं या यूज़ की गई हैं, उनका डिज़ाइन यहाँ पे दिया गया है। इसको आप यहाँ पे देख सकते हैं। इनमें से कुछ जो हैं आफ्टर रॉजर एंड बिफोर रॉजर्स जो हैं वो आगे मैंने यहाँ पे दी हुई हैं। So these are the tubes, X-ray tubes, which are used before Roger. Tubes are designed to produce X-rays. तो ये डिफरेंट डिज़ाइन आपका यहाँ पे ट्यूब का दिया गया है बिफोर रॉजर, and these are X-ray tubes which are used after Roger, and tubes designed to produce X-rays. तो ये यहाँ पे आपकी सारी जो है वो डिज़ाइन दिया गया है एक्स-रे ट्यूब्स का आफ्टर रॉजर। ये भी आपके पास वही है। नाउ we discuss gas discharge tubes and cold cathode X-ray tubes in detail. First of all, gas discharge tube. Prior to Roger discovery of X-rays in 1895, many different types of gas discharge tubes were already in use, like Gessler Crooks, Hetteroff, linear tubes. After the discovery, new types were developed that were specially designed to produce X-rays. Today, gas discharge X-ray tubes are commonly referred to as cold cathode tubes in order to distinguish them from hot cathode Coolidge X-ray tubes that employ a heated filament. But at the time they were being manufactured, they were simply known as X-ray tubes. What these different tubes had in common was the fact that they were made of glass and were partially evacuated. Depending on the type of tube, the residual gas might or might not be air. Tubes designed for X-ray work usually contain air, although some, like smoke tube, employed helium or hydrogen. The configuration of these tubes varied, but there were always at least two electrodes, mean an anode and a cathode, that might or might not be located at opposite end of tube. It was not unusual for X-ray tubes to have three electrodes: a negatively charged cathode, a positively charged anode, and what was known as an anticathode. The latter, auxiliary anode, was usually given a positive charge, but it sometimes had no electrical charge at all. Tubes with both an anode and anticathode were often referred to as bi-anode tubes. When a sufficient electric potential, mean high voltage, is applied across the tube's electrode, a stream of electrons, mean cathode rays, travels through the gas from the cathode to the target. If the tube had an anticathode, it was the target. If the tube had no anticathode, the anode almost always served as the target. When the electron struck the target, X-rays were emitted. The greater the current, on the order of milliampere, supplied by the operator to the tube, the greater the intensity of the emitted X-rays. The higher the applied voltage, the higher the energy of the X-rays, and the more penetrating they became. For diagnostic imaging, more penetrating X-rays were preferred. For therapy, less penetrating X-rays were desired. Several problems had to be overcome when designing the tubes. Perhaps the most important were an overheating of the target when the tube was under heavy use, short and long-term variability in the gas pressure, reversals in the direction of the current through the tube, inverse discharge, and electrical discharge that might puncture the glass wall of the tube, making the target more massive, was the primary method used to prevent it from overheating. Adding one or two special appendages to the tube, regulators or regenerative devices, helped control the gas pressure inside the tube. The primary ways that X-ray tubes differ involve the construction of the target and the design of the regulator. Now we discuss some detail of gas discharge tubes. The application of even a relatively low potential between the anode and cathode will cause any free ions in the gas, electrons and positively charged gas molecules, to migrate to the electrode. Free ions are always present due to interaction with of the gas cosmic rays and background gamma rays. If the potential is sufficiently high, many of the electrons that accelerate toward the anode will pick up sufficient kinetic energy to cause a further ionization of the residual gas. The resulting positively charged gas ions, known as anode canal or channel rays, accelerate toward the cathode, and the freed ions, mean cathode rays, accelerate toward the target. Upon striking the cathode, some of the positively charged gas ions dislodge electrons which join the other electrons accelerating toward the anode. The fundamentals of this process are illustrated in the next series of diagrams or drawings. Of course, in reality, many more electrons and gas ions would be involved than are pictured. First, we see a partially evacuated tube containing residual nitrogen gas molecules. Here is the anode and here is the cathode, and inside is the nitrogen gas molecules. The next drawing shows that one of these molecules has been ionized by background radiation. This is N2 positive with electron here. The next figure, this one, shows the electron traveling toward the anode and the positively charged nitrogen, mean N2 positive, traveling to the cathode. In the following figure, we see that the electron traveling to the anode has ionized two more gas molecules, this and this. As a result, we now have three electrons, mean cathode rays, traveling to the anode and three positively charged gas ions, mean canal rays, traveling to the cathode. In the final figure, this one, we see an electron being knocked off the cathode, this one electron, where the latter was struck by one of the gas ions. For every electron striking the target, a positive gas ion strikes the cathode. As long as a high enough potential is maintained between the two electrodes, the cathode ray beam and canal ray beam is self-sustaining, and the region between the electrodes contain a mix of free electrons, positively charged gas ions, and neutral gas molecules, both excited and unexcited. The positive gas ions traveling to the cathode are less likely than the electrons traveling to the anode to ionize the gas. However, over time, these ions might damage the cathode when they strike it. If the tube was operated at high enough current and voltage, the damage involves sputtering. a process whereby some of the atoms of a material are knocked free when struck by ions. Electrons striking the target do not have sufficient mass to cause significant sputtering. As the electrons travel to the anode, they excite as well as ionize some of the residual gas molecules. This causes the gas to glow. Ionization and excitation will not occur in the gas close to the cathode because the electrons have not had enough time to gain the required kinetic energy. Working of discharge tube. Dear student, for working of discharge tube आपको नेक्स्ट स्लाइड पे एक वीडियो का यूट्यूब की वीडियो का लिंक दिया गया है, आप उसको डिटेल के साथ देख सकते हैं. Here is the link for working of discharge tube. Now typical cold cathode X-ray tubes. The following diagram illustrates the key components of a typical heavy anode cold cathode X-ray tubes. Here is the anode, and it is the anti-cathode mean target, and its cathode, and these are the X-rays, spark gap regulator wire, lever, and its regulator. So these are the key component of a typical heavy anode cold cathode X-ray tube. Now, what is cathode? The original cathodes were flat plates that emitted a broad beam of cathode rays, mean electrons. The resulting X-rays issued from the extended region of the target upon which the cathode rays impinge. Such X-rays produced relatively poor radiographic images. It was soon recognized that better results would be obtained by focusing the cathode rays on a small region of the target. If the resulting X-rays issued from a small point on the target, the images produced by such X-rays would be much sharper. To achieve this, the cathode was curved so that the focal point for the cathode rays was located on the target. For this reason, these tubes were often referred to as focus tubes, and their cathode described as cups. The earliest type of X-ray tube with the focused cathode was the Jackson tube. Professor H. Jackson of King College London is usually credited to being the first to use a cupped cathode in an X-ray tube. Nevertheless, William Crookes had employed focused cathode in his Crookes tube. In the days before X-rays were discovered, the cathode was almost always made of aluminium because aluminium is less prone to sputtering than other metals. Sputtering is the volatilization of the metal that occurs When it is struck by gas ions, the volatile metal which deposits on the glass walls of the tube has a tendency to absorb some of the gas in the tube. This increases the tube's resistance to the flow of current and ultimately shortens its life. If sufficient metal deposits on the tube's glass walls, the latter might darken. In general, a visibly darkened tube is likely to have too high a vacuum, too low a gas pressure to be usable. In almost all cold cathode X-ray tubes, the cathode cup mirror is positioned near the circumference of the spherical bulb portion of the tube. Unfortunately, I have never seen the reason for this clearly explained. The position of the cup along the glass arm that lead to the bulb certainly affect the voltage required to generate a given intensity of X-rays. The further along the glass arm, that is the closer to the bulb, the lower the required operating voltage and the lower the energy of the X-rays produced. The reason, as Hitov noted, is that a static charge will accumulate on glass, mean the glass arm located near an electrode. The greater this charge and proximity of the glass to the electrode, the more resistant the electrode becomes to the emission of the electrons. Perhaps positioning it on the bulb circumference results in the optimal combination of high voltage, X-ray intensity and X-ray energy. And now, what is anode? In many of the earliest tubes employed for X-ray production, for example Crookes and Hitov tubes, the anode was located off to the side at one end of the tube. The cathode rays streamed past the anode and struck the glass end of the tube, which served as the source of the X-rays. Unfortunately, the glass could not hold up under prolonged use. Furthermore, the X-rays were of low intensity. One early solution was to position the anode, a flat metal plate, at the far end of the tube opposite the cathode. In this configuration, the anode served as the target of the cathode rays and the source of the X-rays. And now we will discuss anti-cathode. Most of the early X-ray tubes were what was known as bi-anode tubes, mean they had two anodes, the anode proper and an auxiliary node known as the anticathode. The term anticathode was coined by Sylvanus Thompson to refer to the target upon which the cathode rays, mean electrons, impinge. Sometimes the anode and anticathode were one and the same. but in most of the early tubes they were distinct entities. In most cases, the anticathode was electrically connected to the anode so that both possessed a positive charge. In some cases, the operator might disconnect the anticathode in an attempt to improve tube performance. In many tubes, the supporting arm for the anticathode came in from the side of the tube at a 45-degree angle, and the anode was located along the tube axis. In other cases, the anticathode was positioned along the tube axis and the anode entered the tube at a 45-degree angle from above and behind the target as seen in the above figure. The earliest anticathode were thin and flat metal, for example platinum plates oriented at a 45-degree angle to the tube axis, but these were prone to overheating under prolonged or intense use. Where this was an issue, more massive heavy targets were used to facilitate heat dissipation. For some reason, they were referred to as heavy anode rather than heavy anticathodes or heavy targets. Anyway, these heavy anodes or targets generally consisted of two different types of metals bonded together. A metal with a high atomic number, for example, platinum, osmium, molybdenum, tungsten, served as the actual target for the cathode rays and the source of X-rays, while the surrounding metal, always copper, helped dissipate the heat. There was no clear understanding as to why it was useful to have an anticathode in addition to the separate anode. The general assumption was that having both prolonged the life of the tube and or reduced undesirable variation in the gas pressure. Even though some manufacturers believed that eliminating the anticathode was just fine, they still produced tubes with separate anode and anticathodes because their customers expected it. Eventually, almost everyone recognized that employing both an anode and anticathode served no useful purpose. As a result, late model tubes eliminated the anticathode and positioned the anode on the long axis of the tube opposite the cathode. But by this time, cold cathode tubes had been made obsolete by General Electric hot cathode high vacuum Coolidge tube. That tube signaled the end of an era and the beginning of a new one.
Dear student, here is the end of our today lectures of order X-ray diffraction. Any question regarding to our this lecture or to our previous lectures? You can send me that question at my email ID aslamchemist@hotmail.com, and I shall send you the most appropriate answer of your question as soon as possible. Thank you so much. Allah Hafiz.